Okay, so let's start with the second scenario, which is going to be about the slider crank. So the same way, we're going to just go to here, double click on that. You will find the things already been available for us. We go to the start here, right click and open, and we're going to get the code is going to be open. So that's the crank we're going to work on. So you can see actually that the video, it's not video actually, it's a GIF photo, shows how the movement of the slider crank is going to work. So now we are going to have two different scenarios. The first scenario is going to be the link that hinge to the point O that rotate, and the other one is going to be a link with two ends that rotate. And I explained that in the class last time, and we had that for the other universities as an example in the tutorial. And we're going to see how this stuff is going to work. So again, we need to define some parameters. So this is a demo description. This explores the kinematics and the kinetics of the slider crank mechanism. Now, once again, the kinematics and the kinetics, first one is going to be about the velocities, ignoring the forces, and the other one is going to be about the forces that are doing the motion. So we start with the velocity analysis, which is going to be kinematics of the mechanism, and use the MATLAB live script to capture our working, for example, inserting the relevant diagrams and the computations, and then we're going to have to compare our kinematics computations and those produced by the Simulink Simscape model. The Simulink model also display a CAD-like visualization that animates as a mechanism move. In the second part of this demo, we're going to perform a force analysis, which is going to be the kinetics, by applying the Newton's second law, and we can use the MATLAB live script to capture the workflow. For example, again, to inserting the free body diagram, and the simple math toolbox is going to be used to manage the equations, manipulations, and this diagram, um, this brain drive for the drive model, which is going to be a nonlinear ODE. And then we're going to have a numerically solved in Simulink, and the brain model will response is going to be also compared against the response of the corresponding Simscape model. So we'll start with the demo number one. It's going to be the kinematic analysis of the simulation, and we can do that by open the live script of the PH demo 01 kinematics analysis slider crank MLX. The second one is going to be the kinetic diagram. Again, to open later. Demo number 3 is going to be the kinetic analysis numerically solve dynamic, which is going to be simulate. So these are the system requirements. We're using 2024B because that's the newest one. This actually has been made by 2023 because it was some quite old one. Okay, so that's why we actually use the whole library, because we're going to use many of the library components. So again, start with the first one. Okay, so what we have in this example is that the crank AB rotates with a constant angular velocity of omega AB is equal to 150 radian per second. So the omega AB is going to be for the link AB here. We need to find the velocity of the point P when the theta is equal to 30 degree. This example is quite easy to be solved. We're going to do it by hand calculation. But what's happening is that um, the simulation is going to do multiple iteration, and this will actually going to make a dynamic move, which is away from the kinetic. We're going to have more advanced simulation. So geometry of the relationship is going to be that way. I think that, as I told you once again, we had some example solving this one, because here we can find the velocity at the B, which is going to be perpendicular to the green link, by multiplying the omega by the R value, which is the link AB length. And then between the B and the P, we're going to do the relative velocity equation. Okay, we're going to say that the velocity at the P is going to be the velocity at the B plus the omega multiply by the length BP. Okay, well, which is once again not that hard. So here for this mechanism, we can say that the LAB multiplied by the sine of the theta to make it vertical height is going to be equal to the length of the BB multiplied by the sine of the phi as a function of time. So that's one of the things that we have here. And again, that's what we said about the velocity analysis. The velocity at the B can be found very easy. And then it's going to have two components. We're going to take this make it as a vector. We're going to make it for the second link, which is going to have relative velocity equation to find the two components of the velocity P. Then we can find the magnitude of that. So for the length AB, the velocity, as we mentioned, is going to be just the cross multiplication of the omega multiplied by the length as a vector. And we can come with this equation. Now, for the velocity of the P, we're going to use the relative velocity equation. Oops, sorry for that. The relative velocity equation is going to be that equation. The Vp as a vector is going to be equal to the velocity B as a vector plus the omega, which is z, because rotate around the z-axis, multiplied by the radius of the A slash B. And we can write it down as a vector, multiply it, and we can solve for the I and the J and find the velocity. So the velocity Py is going to be equal to 0. We can write down the equation for the omega, and then we can write the equation for the velocity of the Vp. As we know that the y value is going to be 0 because this slide, the node going up and down, is only going to go left and right. So it's going to have only an x component for the velocity, and we can solve that. So we mentioned that the theta was 30. We're going to keep that. And here we have the omega is equal to 150. The length is going to be 0.2. And the other length is going to be 0.75. Let's go back to the slide, to the sheet, and see what are the parameters you need to find. So the LAB is going to be 0.2p for you, and it's going to be 0.75p for the length of the BP. Omega is 150 and it's going to be constant. Theta is 30, so most of the parameters will remain the same, but yeah, everything is going to be remain the same. Okay, for me, for you is going to be changed, sort of. Now we're going to solve for the phi using the equation 1, compute the velocity b using the equation 2, and then compute the omega bp using the equation 3. Then we're going to calculate for the velocity of the bx using the equation 4. So that's it. Summarizing the results, I'm going to get the answer for that. And actually, you can see that some of the parameters has been already defined here, like the sine, the VP value, and the omega BP can be found. So we are going to display this result by click on display my results. Okay, so I'm going to copy that for later because we need to put them and choose them. Okay, then you're going to compare the result against the Simulink to find the answer. Okay, and we're going to open this system for the crank kinematics SLX. We did that already. We already have it. Okay, and when the Simulink model is going to be appears, click on the run icon, and this picture will be shown here, and you should get the answers directly. Okay, so yeah, let's do that. So open Simulink model for that, and actually that's the Simulink model we're talking about, the crank kinematics, and I can simply click on open. It's going to do the same thing as if I can right click on that and open it. Okay, I'm going to open it from here. Okay, so it's opened on the other side of this of my screen. Okay, zoom out by rolling the mouse. Okay, now we have it open. We need just to click on the run icon, and then we'll see what will happen. Run. Okay, so it says that there's error calculating the parameters for the PRACS dimensions and this model AB caused by unrecognized functions or variable for the LAB. The variable LAB does not exist. Suggested action is load the file into a base workspace. We'll do that. Okay. Suggested action fix. Okay, it seems that it doesn't have it. Oh, that's strange. No, I just need to check the code before I get to do anything. So LAB is already here. Okay, so the LAB is already here. Anyway, let's run this one here. Doing 60% now. Which percent left? I'll try to down this Simulink, and this is MATLAB 1 anyway. Okay, so these are the answers I got. Ah, it's already here. Yeah, so the velocity is minus 15 and 25 for the velocity B. Omega is given here, and the velocity px is minus 18. Okay, yeah. So yeah, so I got the answers, and that's it. Okay, and we've done the first part. Okay, so now let's check how the geometry actually going to be impact the kinematics study. I would like you actually to search that yourself and find the answer for that. Okay, so that's for the kinematic diagram. We just find the velocity at B as uh, by using the code. One of the things we are going to do is here. Let me double click on that. Okay, and it's still loading on the other screen. You can see the things here. Still not responding. Hmm. Well, actually, it doesn't work. Anyway, yep, now it's worked. Yep. So, actually, I don't know how to get this one to you. Um, it's stuck on the other screen, and I cannot find anything actually to catch it. Ah, yeah. Okay, so that's the diagram I got for the different positions and the omega value and the velocity value. Okay, so that's the result you should have for this scenario. And again, if I would like to refresh it, just run it again, and you can see that things will be sketched out for you. Now, that's for the first part, the kinematics. Again, I can play that as a video. Okay. If you would like to change the value for the omega and make it going that way, just make the omega as a negative value, and this will change the direction of your rotation. Now, again, these are the values that we got, so this will be okay. Now, let's go back to the original window we have here. Okay, demo 2 is going to be about the kinetic analysis for the work, and we can get that by opening the demo 2 for dynamic derivation of the slider crank. Now, I will leave the other one live, so again, just click on this one. Okay, the PH02 demo. Okay, so in this one, we're going to have the dynamic equation of the motion of the sliding crank mechanism. And in this example, I'm going to use the Newton's second law to derive the equation motion of the sliding crank mechanism shown below. So what we're going to have is that the joint A is going to have viscous damping. The piston head is going to be experiences a viscous damping, which is going to be friction as the slide. The BA rotational viscous damping coefficient at the point A, and so on. So this is going to tell me exactly what are the forces, because this is a dynamic kinetic solution for the state. So first we can clear that by we say once again type clear. Okay, and the other thing is, if you'd like to clean this one, you just type CLC. Okay, CLC, and this will clean the command window as well. Okay, so we cleared the things, and now we can put that. Okay, and copy, paste, enter. Now the answer is 1 has been shown. Okay, that's we configure our simple computing session. Now, for the kinetic analysis, these are the equation we have. That the kinetic diagram forces is going to be equal to the 3-body diagram forces. And the Ig multiplied by the alpha is going to give me the signal of the moment around the point, around the axis Z. Okay, so we have the synonyms is going to be theta, theta dot, and theta dot dot. And we have the phi dot, and the phi dot dot. So we can have an omega, theta, omega, and alpha for this link, phi, omega, and alpha for the blue link. So the green link components is going to be those, okay, and we can simply find the value for the acceleration of the point G1. Okay, once again, just remember that we have here at the point G, we're going to have normal and parallel components for the acceleration. We can calculate them by using the alpha and the omega. So these are the set of the equation that we have, and at the end, we can have the equation for the velocity at the point P and the equation for the acceleration at the point P. Actually, we can solve this one manually, but again, let's see how it's going to work for here. Dynamic analysis assumption is that the joint A is going to have the viscous damping, as we mentioned, which is going to be the friction, and the same thing happening for the piston, because it's going to have friction that's slowing down, and that's why we're going to have forces on it, and that's what you can see here. This is damping force, the friction force, and here also we're going to have friction force. Anyway, I will leave that for you to read, and we will jump to the simulation directly. You can see that the equations length is going to be too much. We're going to have this simulation block. So the TF I should be create the SL block. We took that already. Let's do it. True, true, false. All good. Next step is upload the system with the Simulink. Okay. Using the demo 3 folder. Okay, so and see what do you want to do? We talked about everything. Yes, we have the assumption we have. Okay, now you can change some parameters, like the parameters for the L1, L2. We set the same value as we have here. Now we need to have some of the parameters that tell me that the length 1 should be less than the length 2. I'm going to leave this one at the moment. Let me check actually what we have in this example. Oh, okay. Now, for this case, we had the velocities for the step number 1, and we're going to have the acceleration from the second scenario that we're working on it right now. Okay, so we're going to leave the same parameters as usual, for me at least, and for you, you have to change it according to your p-value. Initial condition. Now we're going to open the pH model for the crank dynamics, the second one. Okay. And then we only get to run it, and that's it. Okay. So let's run this one. So away from the errors, let's see how the results are going to be. This one, we click run. Okay, similarly for 45 seconds. And Simulink file contains our brain drive models, and also is going to have two-way of modeling the slider crank. Let's call model animation. The log names as the okay here. Okay, so here we're going to find the results by clicking on that link. Okay. Okay, so that's the alpha, that's for Bravo, this is for the theta degree. I can away from that. Okay, so generate the time varying external torque value from here. This will do the simscape model, and this will be the brain drive model, and this will compare the results from the two previous models. So before that, okay, so I did that. Okay, so that's signal one, that's signal two. I don't know why not start uploading the results here. Taking its time. Enjoy it yet. Anyway, let's go back to the original model for the MATLAB. Okay, so sorry, where's our for the MATLAB? It's here. Okay, so click that and to say here, so we have the Simulink file contain both our brain drive model and also the second way of the modeling in the slider crank using the Simscape multibody, what we call the Simscape model. The block name make produce the time varying torque and the force for that. Um, yeah, we show the signal one, signal two. Just simply click on the group one. Explore the simulation results. I did that. One, two, and let's see how it's going to work. Anyway, let's do it again. So actually, I did click on this one. Take me to here. Double click on this one. Bring me to here. Simulate that. Yeah, I cannot see any results here. It's not like what it promised us. Let's see the other one. So I double click on this one. Let me double click on that one. Doesn't show. I shall go to the model and run it. But nothing happened. Data inspector. Got that. Sally Alpha. Bravo. Okay. Uh, let's run that. It's not completing. It's still stopped at 24% only. But I think that actually this shows some of the results that we can find on these graphs. Okay, so maybe if I get to increase that to, I just need 45 seconds. So 45. Okay, now it's completed, and we can repeat that again. And I can see actually this one is working at the same time with these graphs has been made. And I think these are the results that we would like to have. Okay, now these are for the R value. I'm sure that we can find something for the acceleration because that's what we would like to find. We can actually print here show uh, my results and it should give me the same answer um, as I show everything. Okay, so these are the output. Open selection. No. Does it have something about the float? Float. Okay, so that's the value for different parameters we can have here. Okay, yeah, I think that should be enough. You find the rest.